So we're starting to get an idea how hypothesis testing works, and it's based ultimately on the p-value. Let's recap a little bit, talk about what the p-value means, which is one of the hardest things to understand about statistics, and then we'll look at an example of how we might actually try to calculate a p-value. So hypothesis testing is based on first formulating some hypothesis, formulate an alternative hypothesis, formulate a null hypothesis, which is a counterpoint that says there's no effect at all going on here. Collect some data, and then we have to ask ourselves, is that data consistent with the alternative hypothesis? Is it consistent with the null hypothesis? What does that data provide us evidence for? Now, the next thing that we're going to do with the data is we're going to calculate the p-value. Now, let me remind you what the p-value is. The p-value is the probability of getting such evidence by chance if the null hypothesis were true. Basically, it's the answer to the question, what are the chances that this kind of evidence could just be an accident? And if the chances of this kind of evidence really just coming accidentally are good, if that's likely, then we don't really have very good, strong evidence in favor of our alternative hypothesis. But if it's very, very far-fetched that random chance would produce evidence like ours, then the null hypothesis is not credible, and we will reject it and go with the alternative hypothesis. So this is where our hypothesis test branches into two possibilities depending on the data, right? If the p-value is very small, that means it's really not likely that we would get evidence like ours from chance alone if the null hypothesis were true. And so we reject the null hypothesis. This is what we want to do in statistics. We declare we have statistically significant evidence for the alternative hypothesis, and we publish our results. Okay, so this is, from a scientific and statistical point of view, this is what we usually think of as a good outcome. But of course, depending on what we just proved, it could be a good thing or a bad thing. If the p-value is large, that means that the probability of getting such results from simple chance alone is actually pretty good. And that means that the null hypothesis is still a credible explanation for what happened. In other words, it could be there's no effect at all going on here, and it could be that our data and our so-called evidence could really just happen from simple coincidence. And so the data could just be coincidental. So we have weak or no evidence for the alternative hypothesis, and that means that's kind of a bummer, but we should probably publish that anyway so people know what we did. So these are the two outcomes based on the p-value. Now, what you might ask here is, well, what do you mean by small? And what do you mean by large? Well, it depends how strict you are and how strictly you require evidence for things. And that's what depends on alpha, right? The level of strictness you need in order to prove something, in order to reject an explanation by coincidence, depends on how strict kind of evidence you need. And that is the value of alpha. So when we say that the p-value is small, what we really mean here is that if the p-value is less than this value alpha, which is how strict you are about demanding evidence for things. And if the p-value is large, what we really mean here is if the p-value is greater than alpha. Now, in practical terms, alpha is very often chosen to be 0.05. So very often 0.05 is the value that is the cutoff. And so 0.05, and there's nothing really magical about this, but just culturally, we've kind of focused in on 0.05 as a pretty decent value of alpha, pretty decent demand to make on your p-values. And so in practical terms, this test often boils down to comparing the p-value to the specific value of 0.05. If it's less than that value, that means that coincidence is not a good explanation for our data. Something really is going on. We reject the null hypothesis. If the p-value is greater than that value, then that means coincidence is still a plausible explanation for the data. And so the null hypothesis is credible, and we haven't really proven anything with our test. So again, this is the structure of a hypothesis test. But again, it depends on the ability to calculate the p-value, which is the thing I keep postponing. So now I want to indicate, at least in principle, how we can calculate a p-value by a process of simulation. So in order to do that, I'm going to introduce an interesting hypothesis test, which is this managerial bias test. So I want to remind you of this study from the 70s, in which we have some managers making some promotion decisions about several files. And the files are tagged. The files are real files, but they are randomly regendered files, meaning the names and genders of the files have been changed to sort of fictitiously represent men and women. Even though they're sort of fictitious, we'll refer to them as men and women. So we have 48 files, and the manager's responsibility is to recommend for promotion or recommend for not promotion each of these files. So let me explain how this works. We have 48 files, and they are 24 men and 24 women. And the managers, they recommend for promotion. Or, I mean, they make decisions whether to recommend. They recommend or not these files for promotion. So the alternative hypothesis is that the managers are going to be biased against the women. And the null hypothesis, so there is an opposite hypothesis here, which is that the managers will be biased against the men and in favor of the women. But the null hypothesis is the interesting counterpoint, and that is that the managers are going to be unbiased. Notice the null hypothesis is, in a way, the ideal here. The managers, so we actually, in a way, we would hope that the null hypothesis would be true. Now, these hypotheses can be phrased in terms of the probabilities here. We're going to write the probability as P sub W for the women and P sub M for the men. That's the probability of getting recommended for promotion. So here, the alternative hypothesis will be that the probability of women getting recommended for promotion is actually less than the probability of men getting recommended for promotion. Or maybe I should say proportion. The proportion of women recommended for promotion will be less than the proportion of men recommended for promotion. And the null hypothesis will state that the proportion of women recommended for promotion will be equal to the proportion of men recommended for promotion. And so these are the two competing hypotheses. Now, these are population proportions. These are not p-hats. These are population proportions. And they really refer generically out there to all the millions of files that the managers might have read. Okay, so this is not actually the data proportions, but the generic proportions out there. So, so we've clarified the alternative and the null hypothesis, and now let's the experiment has to happen, but we have the data, so let's describe the data. So the data says that 21 men, 21 out of the 24 men, were, I'm just going to say promoted. In fact, they were recommended for promotion, and 14 of the women were promoted, and this is the real data that came from the study. And if you look at this results, then your knee-jerk reaction might be like mine to say, well, you know, they're showing bias, right? It certainly looks like they're showing bias, right? Because they're 24 of each, and 21 out of 24 men were promoted, 14 out of 24 women were promoted. So from this, we can calculate the actual proportions, but the actual proportions within the sample will be p-hats, right? P-hat for the women will be 14 out of 24, and p-hat for the men will be 21 out of 24. And certainly, p-hat for the men is greater than p-hat for the women. And if you think it's a slam dunk, then you haven't watched the previous videos. So this is the data proportion, the sample proportion of the women and the men, and certainly for the men is greater. That does not just prove the alternative hypothesis, because there's a competing theory. The competing theory is that the managers are actually unbiased, and that these differences appear due to random chance. And this is a plausible theory. We just need to assess how plausible. We need to assess what are the chances that that would happen. So let's emphasize what the p-value means here. So the p-value is the probability under the null hypothesis. So the p-value is measuring if the managers were unbiased. So what would be the probability of getting this much evidence of bias? And the fact of the matter is, you could, in principle, get this much evidence of bias, even if the managers were unbiased, right? It could just coincidentally work out that way. It could just coincidentally work out that 35 of these files are good files and they're promotable. I'm saying 35 because 14 plus 21. 35 of these files are good files and they're promotable. And when the researchers randomly assigned genders to these files, they just happened to fall this way, so that the male gender was just randomly and accidentally assigned to 21 of the good files. And the female gender was just randomly and accidentally assigned to only 14 of the good files. And it could be the result of a coincidence here. The question of the hypothesis test is, what are the chances of that? The p-value is meant to be a direct measure of the probability of that. Now, that's hard to measure directly. And what we're going to do right now is we're going to show how we can use a simulation to start getting at that data. And then I'm going to use a simulation by hand, which is kind of slow. And then we're going to move to the computer to see how we could accelerate that simulation and make it so that we could actually calculate the p-value fairly precisely by simulation. So let me explain how we're going to do this simulation. The simulation is trying to assess the p-value, which is what would happen if the managers were unbiased. And so the simulation is going to show no bias whatsoever, and we're just going to let the cards fall as they will. The literal cards, we're going to use cards for this simulation. So what I have here are 24 red cards, and those represent the 24 women in this simulation. And then I have 24 black cards, which represent the 24 men in this simulation. What I'm going to do is I'm going to shuffle them together. This represents my pool of men and women. And then I'm going to randomly select from this pool some 35 cards. Okay, I'm actually going to just, because it's simpler and faster, I'm going to exclude 13 from 48 to make 35. So after shuffling these together, I'm going to throw out 13 cards, and then I'll have my pool of 35 good files. And then what will we see? Well, I'm showing no bias, right? I'm just shuffling these, and that's important. That means that I really am being faithful to the null hypothesis. I am being the perfectly unbiased manager here by just shuffling these together and picking 35 files. So that's important. I'm showing no bias. So I'm just going to start not looking at these cards, but making sure that they're well shuffled. I'm going to exclude 13. So that's 13 excluded, and I'm left with 35. These are the 35 which are promotable files. But because I started with a perfectly fair shuffle process, what I've done is I've modeled the behavior of the manager at picking out 35 files without any bias. These are the 35 files that I can recommend for promotion. And so now it just happens that we've got a bunch of black ones here, a bunch of red ones. So now what I can do is I can sort out these 35 files, and I can see, how did it break down? How did I break these things into men and women? So now I'm going to separate the men from the women. These are the men recommended for promotion, and these are the women recommended for promotion. And now what we need to do is we need to count them, okay? So let's go through and count them. I'm going to count them by fours. 1, 2, 3, 4, and that makes 18. I'll fan them out, and if you don't believe me, you can pause the video and count them. That's 18. Now, if I did my counting right, then this is recommended. This is going to be 17. So pause the video and check me, 17. So that makes sense. That makes perfect sense, right? 35 files, men and women randomly. We shuffle them, and we get 18 men and 17 women, which is as close to fair as you could get if it were an unbiased process and we're getting 35 files, right? So this is what would happen if it were random. It would tend to be fair. Now, what I'm going to do, I'm not rigging this game. It's just working out the way that it is. What we're going to do next is we're going to shuffle it again. So what have we learned? Of course, an unbiased process is likely to produce outcomes that are close to fair, right? It couldn't be exactly fair because it would be 17.5, but as close as possible to fair. Of course, an unbiased process is going to do that. So what I'm going to do is I'm going to do these results again. Now, am I going to get exactly the same thing? Maybe. Am I going to get something slightly different? Maybe. Am I going to get something dramatically different? I don't know. Probably not, but maybe. Okay. So again, I'm gonna exclude the right number of files so that I've quickly chosen 35. So this should be 35. And then again, I have my 35 promoted. One more time, we're going to select out the cards that are women and the cards that are men, and we're going to see how this goes. I dropped one. I'll pick it up in a minute. Okay, so remember the black represent the men and the red represent the women. And here we go, breaking this up. All right, let's count the women. I don't know how many that is. Pause the video and check me. 1, 2, 3, 4. Okay, so I get 18 women and 17 men. So I'm going to take for granted that my count was right, and that must be 17. So 17 men and 18 women. So that was just about exactly the same. It's just about exactly fair. Now, what have I illustrated? On the surface, not much, right? I mean, of course, it's going to be about equal if it's a totally unbiased process. And this has been a totally unbiased process. And this is not producing biased results like this. And so what I'm producing is a little bit of preliminary evidence that a totally unbiased process is not likely to create results that are as skewed and biased as what we're seeing there. And so what I'm doing is I'm producing a little bit of preliminary evidence that the p-value actually is a kind of a small value, because an unbiased process is not likely to produce this. An unbiased process is most likely to produce results like 17 versus 18, 18 versus 17. Are these the only results that can happen from an unbiased process? No, not exactly. I could certainly get 19 versus 16. That's also possible. On the occasional, mistake, well, not mistake, but an occasional just coincidental by chance, then I could produce results like 20 and 15. It seems less likely that I would produce results like 21 and 14, or even more skewed, like 22 and 13, 23 and 12, right? It seems less likely. Now, from my two little experiments, I can't exactly calculate yet the exact probability of doing this. But what if YouTube videos can be long too, right? What if instead of going on with more theoretical work, I just keep doing this, right? And I force you to sit through hours and hours and hours of this nonsense, then sometimes we will see some other results. If I do this 1,000 times, my hands will be exhausted, right? You will be tired of watching, but if I do this 1,000 times, then we will see a wide variety of results, and we will see which ones are common and which ones are rare. And from that, we will have a large pool, and we will say, you know what, in that 1,000, sometimes stuff like this does happen. We can count up how often it does and divide by 1,000, and we'll have an empirical measurement of the probability of getting results like this just by chance. Now, obviously, I'm not going to do this by hand, and I'm not going to do this with a pack of cards, but we can do this using a computer. We can ask the computer to resimulate all of these experiments. And it's just as easy for the computer as it is for me, because the null hypothesis of the managers being unbiased makes everything very simple to simulate. All we have to do is have 24 things. They don't have to be playing cards. 24 things of one type, 24 things of another type, and we have to be able to pick out 35 at random and count them. We can use a computer to do that, and that's what we'll illustrate next. When we use that computer to do that, we'll be able to do this thousands of times, and we'll be able to assess by simulation the actual p-value that helps us decide the result of this. So we're going to switch to the computer program to do this, and we'll see how it goes.